you'll remember from your Gen Chem class that there are a lot of times where you can identify where a structure will have what we call resonance, right, or the delocalization of electrons. And usually you will identify this by, oh, well, why does that oxygen have a negative charge but not that one? And so you can actually draw it with either one of them, and it's a combination of the two, et cetera, or where a double bond goes. So we're actually going to go over 4 different types of situations that are a really telling factor of whether you'll have resonance or not. So we're going to jump right in, hopefully do this pretty quickly. The first type, and I know I usually type out like a typed document, like a Word document or PDF of notes. This one's just a little bit easier to draw through, just simply because we're going to be doing a lot of drawing today of bond line structures, so it's good practice. So the first type of structure or characteristic that we should have, I should say, would be an allylic cation. Definitely put 2 L's. There we go. Which is a positive charge adjacent to a pi bond. So positive charge adjacent to a pi bond. Right, so something that looks like this. Right, so we have our pi bond here. This carbon has a positive charge. It's 1 spot away, so this is the multiple bond, and then bam, 1 spot away, we have a positive charge. So what we do, and you'll remember from the analysis of formal charge and oxidation states video that we talked about arrow pushing. Just another friendly reminder, full arrow means 2 electrons, half arrow means 1 electron, and we'll get to that in radicals much later in the Organic 1 videos. We will use arrows to show the movement of electrons to kind of justify where we're putting our bonds or where we're putting lone pairs or what's going on, right? So we can keep track of all of our electrons. Helpful. Right? So what can happen in this scenario is the electrons here can actually jump to being between these 2 carbons. So if we numbered these carbons, 1, 2, 3, and 4, these pi electrons could actually jump to be between carbons 2 and 3 rather than be between carbons 3 and 4. And we show that using an arrow from the center of the multiple bond to the center of the carbon-carbon single bond. So remember, resonance arrows, double-headed arrows, draw the same skeletal structure, and we will put the double bond here, which means that now we have a positive charge on this side. So that is how we do resonance structures for allylic cations. So remember, cation 1 position away from a carbon-carbon double bond. We're delocalizing those electrons through a pi system because the pi system can now be spread over 3 atoms, not just 2. In the next video, we'll be talking about ways to draw more complicated resonance hybrids. For the sake and purpose of this example, though, right, we go and show where our bonds actually are. So we have the same skeletal structure if we were to draw a hybrid. Same skeletal structure, 4 carbons. There's a positive charge here in this situation and here in this situation, but it's not there all the time. So we say there's a partial, and that's a really terrible lowercase d. Still bad. Partial positive at both these carbons, right? Because it's not there all the time. Like technically it's half the time here and half the time here. So it's not a full positive. And then remember, it's kind of like 1.5 bonds across these. So instead of drawing in full bonds, we draw in dotted lines. And this is a relatively simple resonance hybrid. We show partial charges, by the way. This is a it's a lowercase delta. So Greek letter delta, meaning change in partial charge, though. So that is an allylic cation. And we'll actually go to the next page for this. The next thing, so the first one was called an allylic cation. That's positively charged. Now we're going to go the other way with the allylic position. And we'll go negative. And what do we associate negative with? Electrons. So we will talk about the allylic lone pair. Yes, very exciting. So again, this is lone pair adjacent to a pi bond. So let's take a molecule that is going to give us a lot of good practice in drawing our bond line structures. So we'll take this, really fun, and just goes to show you, it doesn't have to be a carbon-carbon double bond to have resonance. It can be a carbon-oxygen double bond. So something that you haven't seen yet, so this is fun. We're also throwing some nitrogen in there, so that's interesting. And we're going to do this in the same way that we did the last example. So again, instead of drawing it from the center of a multiple bond to a single bond, we're going to draw it from the lone pair to the center of the carbon-carbon single bond. Now, if we put a bond in here, right, if we put a bond in there, then this carbon would have 1, 2, 3, 4, 5 bonds. Well, that's not going to work, right? So there actually has to be 2 arrows that go within a allylic lone pair, right? Because it has to be adjacent to a pi bond, right? Has to be adjacent to a pi bond. So one of those bonds, instead of having that extra bond, one of those bonds is going to break and go to the outside atom. So resonance arrows in. Nitrogen, we've got our 2 ethyl substituents here. Remember, ethyl meaning 2 carbons, right? 1, 2 carbons bonded to a nitrogen, so nitrogen, carbon, carbon, nitrogen, carbon, carbon. Then we have the same skeletal structure. Remember, we broke one of those bonds, put a 3rd lone pair on that oxygen, placed a multiple bond from the nitrogen to the carbon, and then nitrogen only having 4 electrons from bonds gives it a formal charge of +1. Right? You'll notice that the formal charges always add up to be the same as the original molecule. So, if we look at the last example, formal charge on this total molecule was +1, formal charge on this total molecule is +1. We're good. Formal charge on this total molecule is 0, formal charge on this total molecule, right, +1 and -1 come out to 0, so we're good. So, that is all we are drawing for this. That's the only resonance structure, so now we'll draw the hybrid. Right, so we're just going to draw in that single bond structure. And then, just like we did last time, right, so at most, or at least, excuse me, there's 2 lone pairs on oxygen, at most there's 3. So at the very least, you'll find 2. So we'll draw in those 2 lone pairs. Remember, we indicate partial bonds with those dotted lines to show that it's a little bit more than a single bond, but a little bit less than a double bond. And actually, let me draw that second one in a different spot, so it's a little more obvious. Just so it really shows you that that's there as well. And I kind of want to extend that line. Perfect. So now we draw in those partial charges, right? So nitrogen at most has 1 lone pair, at least has 0, so we don't draw any there. There's a positive charge on nitrogen in one structure, so we put a partial positive. And again, I'm not great at making lowercase deltas, so I try my best. But I will kind of go back if it could be unclear. And then at this oxygen, remember, we have a negative charge, so partial negative. So just giving you a second to finish writing that one down. I'd like to do one more example of an allylic lone pair just so we can get used to those 2 arrows. So how about something like this? We'll go double bond here and lone pair here. So, different example. Remember, so we're going to draw an arrow from the lone pair to the adjacent carbon-carbon single bond. We'll also draw the electrons from the current multiple bond going to the atom that's not participating. So If the double bond ends up here, this carbon's still participating in that double bond, so go to the atom not participating in the double bond. Because I realize saying the outside atom does not always make sense. So remember, so we move the double bond to here. Lone pair negative charge goes there. So it's a little bit more awkward because our arrows are both kind of in the same place. We're going here and coming this way. Remember, it's from, so if electrons are going out to an atom, it's just going to become from a bond to a lone pair. We draw from the center right to that atom. So the arrow pointing exactly at this carbon. If we're making a bond, we go from the electrons to the center of that carbon-carbon bond, showing that they are distributing along and making a multiple bond. If we're going to draw the hybrid, right? Same skeletal structure. Sometimes the double bond is here, sometimes the double bond is here, and we have lone pairs and negative charges at carbons. So let's number our carbons. We have negative charges at carbon 2 and carbon 4, so 1, 2, 3, 4. So we can write in partial negatives, and we can draw in those partial bonds as they are between carbons 2, 3, and 4. So, just a second example for an allylic lone pair. Actually, let me give you a second to get that all written down. Okay. So the next type that we have, or the next scenario, is, and there's not like a flashy name for it, and it's called the lone pair adjacent to positive charge. So lone pair adjacent to a positive charge. And let's use another good practice scenario for your bond line drawings, remember. So this is, so most of you are like, it's a pentagon. No, it's a 5-membered nitrogen heterocycle, or just a 5-membered ring. 1, 2, 3, 4, 5 members in that ring. I could actually make that last line a little bit better, which I kind of want to do. Oh, I messed it up. Never mind, we're leaving it. So those resonance arrows, again, are just going to show that lone pair is coming down, making a double bond here. It's going to be a lot like your Allylic cation. And I'm drawing my skeletal structure in first, so then I can be a little bit more specific on where I'm putting that double bond. So remember, the positive charge moves over, double bond is created. Obviously, the positive charge wouldn't end up on a carbon. So remember, for the allylic cations, positive charge moves 2 spots. Lone pair adjacent to positive charge, it moves 1 spot, right? So 2. So if it moved 2 spots, it would go like here or here. Now it just goes to the nitrogen. So from here to here, double bond. It's a really easy hybrid to draw, so we won't worry about drawing that for the moment. I'll just do one more example. This one's pretty easy. So we've got another lone pair adjacent to a positive charge. We're going to show those electrons hopping down, making a bond. So remember, those electrons are coming down. So from the lone pair to the center of the carbon-carbon single bond. Resonance arrows, same skeletal structure. No. One lone pair stays on the oxygen. Oxygen now has a positive charge. So, very cool. Let's draw the hybrid for one of them. Let's just draw it for the top one. So let's go hybrid, since you love drawing pentagons. So we're going to draw our skeletal structure here, partial positive both on this carbon right here and this nitrogen, with a partial bond there Don't really touch the 5-membered ring at all. Kind of just hangs out. Let's go on to the last type of scenario that's going to give rise to resonance for us. And it is called a pi bond between two atoms of differing electronegativity. So it's basically the opposite of the situation we just had above. Okay, so in the situation above, by above, I mean on the last page, because I thought I was doing this on lower on the page, but I was not. So by that I mean if we have a pi bond between two atoms of differing electronegativity, we're going to start with a double bond and end up getting rid of that. In this top scenario, I'm acting like it's on the same page. I'm switching screens. I'm sorry. In this previous scenario, we started with no double bond and ended with a double bond. So I'm going to say, and I'm going to denote, so if you need to replay the audio again to write this down, it's a pi bond between two atoms of differing electronegativity. So pi bond, can't write, bond between differing electronegativity. And we're going to take an example because that sounds really, really complicated, but I promise it's not. So we've got an aldehyde here, good functional group review, right? And remember there's two lone pairs on that oxygen to start with. We'll draw them in. So like last time, we went from lone pair to making a double bond. Since this is opposite, we're going to go from a double bond to making a lone pair. And I will make that arrow look a little bit better by putting it on the other side. Resonance arrows, hydrogen doesn't move, oxygen gets the negative, carbon gets the positive, because oxygen is significantly more electronegative. Maybe not significantly, but it is a good deal more electronegative. If we want to draw the hybrid for that, since we're getting good, and we're going to go over more steps for this, I'm just showing you this right now because you will eventually rewatch this video because you're having so much fun taking these notes. Drawing in the skeletal structure, at most two lone pairs on this oxygen with a partial negative charge. This carbon, of course, has a partial positive charge, and we'll put a dotted line between the oxygen and the carbon to show a partial bond. One more example for this scenario to give resonance. We'll throw a nitrogen in there this time. Whoops. And let's go ethyl on the other side. And 1, 2, 3, 4, 5. Got it. So, pi bond between two atoms of differing electronegativity. Again, so noticing the trend, right, we're going to draw the arrow from the center of the double bond to the more electronegative atom, i.e. the one that wants the electrons. Nitrogen happens to be more electronegative than carbon. Actually, let me redraw that bond so it's a little bit easier, much better. So we're going to draw that arrow towards that more electronegative atom and draw our new structure. So now nitrogen has two lone pairs, negative charge, and this carbon has a positive charge. Draw the hybrid again, and we have one lone pair on the nitrogen, a partial negative charge on the nitrogen. Here, let me draw that actually the other way around. Lone pair down here, partial negative, and a partial positive on that carbon with a dotted line between the carbon and the nitrogen. And that is a pi bond between two atoms of differing electronegativity. So something that you need to remember, just really quickly, is that when you're drawing resonance structures, a single resonance structure should have no more than two formal charges. Formal charges meaning charges on atoms, right? So this one, 0 formal charges, this one has 1, 2. This one has 0, this one has 1, 2, okay? So remember, if you can draw a resonance structure and you go through and you're drawing If you have 3 formal charges, you've done something wrong. So I'm going to write at the top of the page, single resonance structure should have no more than 2 formal charges. So I want to look at a couple examples really quick, and then we're going to be done. We're going to draw an ester. Know you're doing your functional groups. So this is what an ester looks like. And we're going to draw our resonance structure. So we'll draw in some arrows as well. Right? So first, we can do pi bond between 2 atoms of differing electronegativity. Right? So we can go here. Actually, I'll use the red. Really bad O. Better. So remember, we did this example in the last screen. We did this example. So that second oxygen doesn't change. Now we have lone pair adjacent to a positive charge. If I drew in the lone pairs, now we have lone pair adjacent to a positive charge. Cool. And I'm going to use red for the arrows. Actually, no, I'll use green for this arrow, just so we don't get confused. Right, we create that multiple bond there. So now we have another resonance structure, and we'll draw that in red. I'm trying to make these lone pairs really easy to see. So I'm going to my greatest extent to try to make them dots. Later in videos, I might just draw lone pairs like this. You'll be used to it by then, but I want to make it really obvious for resonance because they're very important. But then also, we have a lone pair adjacent to a pi bond, or an allylic lone pair, and I will draw those arrows in blue. Remember, we make a pi bond here, and then we break that pi bond. Now I'm just kind of drawing through this quickly because I want this video to be done for you guys relatively quickly. And then this structure could be drawn with an arrow like this, going to that one. So we never had any more than 2 formal charges in these structures. And that's good, because you should never have more than 2. So let's look at an example that is not so great. So, not so great example. Here it comes. That's sideways, and I'm not a fan. There it is. So let's put a lone pair out here on this carbon, minus, and let's switch it up. Let's double bond a nitrogen. So, we have a pi bond between 2 atoms of differing electronegativity. So we're going to draw the arrow from one of those bonds towards the more electronegative atom. Resonance arrows, here we come. So, let's do this in steps. Okay, we're just going to draw the skeleton of what we have. So draw everything in the same. Actually, no, we're going to take those lone pairs off, draw them a little bit nicer. So, what have we done? We've taken this pi bond, this double bond right here. These 2 electrons have gone into the nitrogen. So we're going to add a lone pair to the nitrogen. That's step 1. So that means nitrogen has 1, 2, 3, 4, 5, 6 electrons. It gives it a charge of -1. Now, you may be thinking, okay, well, we're done. Turns out we're not. Okay, so think back to that first example of a pi bond between two atoms of differing electronegativity. And remember that you start with no formal charge between those atoms, and you end up with a formal charge on both. Right? So we start out with a no formal charge here, no formal charge here, neutral, neutral. We have a negative formal charge up here, so we have to have a positive formal charge on this carbon. This carbon right here. Now this resonance structure has 1, 2, 3 formal charges. Okay? So this resonance structure is what we would call a minor, or, well, actually, let's not get into major minor resonance contributors right now. Scratch what I just said. Through the power of editing, I would take that out, but it's pretty difficult to do that with the particular program I'm using. So, scratch that. Only draw resonance structures that contribute to the hybrid or ones that have no more than 2 formal charges. This one has, of course, 1, 2, 3, so we can't use that. Okay? So, make sure in your structures that you're not breaking any single bonds. Single bonds don't break, they stay the same. Remember, we always say, draw your skeletal structure, start with that, and go from there. So I'd like to do one more whole problem that just kind of lets us practice. So one more practice problem. We'll use, let's say, nitrogen this time. So let's draw on our starting structure. And we'll go an ethyl on this side. I'll draw that nicer for you. H. Let's put a double bond, positive. And we'll put a double bond there. Okay, let's just do this, right? So what are we going to do first? We're going to start with pi bond between two atoms of differing electronegativity. So this nitrogen, so in the previous example, right, we said, okay, so no formal charge goes to 2 formal charges. Really, both the formal charges just change, right? The more electronegative atom goes down, the less electronegative atom goes up. And by going down, I mean going negative from what it was before, and by going up, I mean going positive from what it was before. So in the case of this nitrogen, it's already a positive. So when I put 2 electrons on that nitrogen, and there's a hydrogen. Now there's 2 electrons, right? It goes from positive -1, now it's just neutral. Now nitrogen's just hanging out. It's having a good time, right? So nitrogen's been taken care of. Remember then, this carbon that originally had another bond to it now gets a positive charge. And remember that we started with a double bond between this methyl substituent down here, or this line, and this line. Right? So we're going to put the double bond here. Now, you may think, okay, well now I've seen something just like this. This is an allylic cation. Remember, so we're 1 position away. That is not the pointer. We are 1 position away from the double bond. So double bond, cation. So those electrons come over here. And we can draw one more resonance structure. I'll draw it nicely for you. So now we have the double bond here, and the carbocation is there. We'll do practice drawing the resonance hybrid. Again, in the next video, we're actually going to go through a stepwise process of drawing the hybrid. So that's actually where I'm going to address the specifics of it. But by then, that'll just be a review. Again, we start with our skeletal structure of what's the same. So we're going to draw in all those single bonds. Nitrogen's there. Gross. That's here. We always have a hydrogen hanging out above that nitrogen. Now, at the very least, nitrogen has no lone pairs. So unfortunately, there's no lone pair we're going to draw on that nitrogen. And then the double bond is actually in all 3 of these places. So here, here, and here. So we delocalize that double bond across those atoms. So now, instead of just being between these two and these two, the pi system can now be delocalized between these two as well. So we're very stable. Yay, we're very happy. So let's put in those partial charges and call it a day. This video is way longer than I wanted it to be, but welcome to learning organic chemistry. Organic is actually, oddly enough, it is one of the only places where there is a direct correlation, no matter how awesome you are at it. There's a direct correlation between how much time you spend really engaging with the material and how well you do. So, unless you're just ridiculously gifted in organic, in which, congratulations to you, I'm very happy for you. But we'll draw in those charges anyway, and we will call it a day for resonance. Remember, there is no, so you may be thinking, a lone pair on the nitrogen. Yeah, so there's no lone pair here, so we cannot draw it in. So partial positive, partial positive, partial positive. And that should do it. Awesome. Thank you guys for being so patient through the resonance video. Well, actually, we'll get obnoxious here. We'll do that. And really, this is stuff that I hope was pretty straightforward and clear. Again, with the terminology, just remembering allylic being one spot away from a double bond, that resonance is delocalizing those electrons through the pi system, and that drawing that resonance hybrid is the most accurate way to see how the molecule exists in regular passerby of organic chemistry. So, I hope that video was helpful. I know it definitely wasn't too short, but hey, it's a really important topic, and it's going to come up a lot in Organic 1, Organic 2, and other applications of reactivity in organic chemistry. So, that being said, I will see you next video, and thanks.